Welcome to the Scientific Method Part 3 notes, bringing together the trifecta that we started at the beginning of the course and going to the end of the course of Scientific Method 1, 2, and 3. So once again, viewing science as a culture, we are digging down deeper, and we are getting to not the exact core of everything, but getting to a deeper understanding and finally bringing together everything that we've been learning about in this course of the logical reasoning, of deterministic, everything fun reasoning, quantitative reasoning, scientific reasoning, statistical reasoning, and bringing it to this forefront of, well, how do we end off the actual scientific method for running experiments and analyzing the data, which will be the main focus for these notes. And once, as always, let's shrink me down to this bottom side, and get started. And I don't know, maybe I should do all these notes in a weird, cheesy, game show host voice, 'cause I wonder how long people could last learning about the Scientific Method Part 3 with me using a voice like this. Not sure. Maybe I should go back to my normal voice. Or maybe I should continue. Yeah, I'll go back to normal. Now remember, we got the scientific method, and we've seen this chart here multiple times, talking about kind of like algorithm, procedure that we could go through, starting from asking a question, down to coming to some kind of conclusion based upon our evidence, and each previous step acting as a premise in our long, deductive reasoning proof as to why we think our answer is a possible solution for showing a cause and effect that we are looking for throughout the entire scientific method, and then having other people repeat this and back this up. Now, for the phase of these notes, we are sticking more now down to, you've constructed your hypothesis, you have a good understanding of statistical reasoning and stats, and now you want to design your experiment to test your hypothesis and predictions. And you need to know, well, how do I set that up before I start doing everything? How do I deal with step 3 of that establishing causality for dealing with the non-spurious cases? And how do I collect that data, and how do I finally come and analyze that data? And we've seen a little bit of this before in the previous notes, but this is now just to bring it all back together in a science kind of context. And as always, too long didn't read. Let's have a little introduction to experimental data collection from one of my favorite series from YouTube in case of science, and quick learning, the crash course that you've seen multiple times before.
Hi, I'm Adrienne Hill, and welcome back to Crash Course Statistics. Famous tech guy and likely future space dweller Elon Musk once told interviewers that there's a high probability that we're all living in a simulation. Now that might sound outlandish, and it's an interesting statement about probability, but today we're going to focus on the simulation part. Elon Musk, as well as some philosophers, futurists, and technologists, argue that it's entirely possible, probable in fact, that in a few thousand years we will be able to create simulations like World of Warcraft or Minecraft that are so real they'll be indistinguishable from real life. Living in a world like that, there's no way for you to tell if you're living in the true world or a simulation, or maybe a simulation inside a simulation. If we were living in Musk's vision of a future world, anytime we wanted to test something, like whether that bus would have splashed us if we didn't stop to answer a text, or whether the new drug we invented can cure lung cancer, all we would need to do is run 2 identical simulations. In one simulation, we'd give people with lung cancer the new drug and watch to see what happens, taking notes on things like lung capacity and remission rates. While that's happening, we'd do exactly the same thing in another simulation, except we give patients a placebo drug, something that looks and feels like a real drug, but isn't, and we'd record our results. Once both simulations are done, we'd be able to look at our data and have a good idea of whether it works. Now, we can't yet run a parallel universe just to satisfy by our curiosity about whether the amount of time we spend sleeping next to our cell phone increases our chance of brain cancer. But we are doing the next best thing. Researchers have started using simulations to study cancer treatments, to predict the impacts of climate change. Researchers are using VR to simulate disaster situations and to help train people how to respond in earthquakes or floods. Thanks, Thought Bubble. Still, we need other ways to answer the burning questions that keep us up at night. And until scientists can pull through with the necessary technology, we're limited to two main methods of collecting data to answer our questions. One way to get around our inability to create and destroy universes at will is by using experiments. Experiments try to mimic parallel universes by taking the one universe we do have and splitting it randomly into groups. Imagine a high school where test scores are low, and we want to see whether buying cappuccino machines for students' families will improve test scores. We don't have two parallel versions of the high school to test our idea, but we can randomly split it into two groups. One group's families will get the free cappuccino machines and the others won't. And then we let life go on, just like in the simulations, and we record the test scores of both groups. Because we randomly assigned each person's group, every single family had an equal chance of being in the cappuccino or in the no cappuccino groups. Randomness allows us to claim that before the cappuccino makers were given out, there were no systematic differences between the groups. Usually, researchers will use a random number generator to assign subjects into random groups. Random assignment reduces the chance that the bias of the people running the experiment will affect the groups. For example, it prevents them from doing things like putting subjects who they think will respond to caffeine in the cappuccino group and those who don't in the no cappuccino group. It also makes it impossible for people to choose their own groups. That way the coffee lovers don't all sign up for the free cappuccino machine while the tea enthusiasts don't. These two problems are called allocation bias and selection bias, respectively. Because of randomness, it's unlikely, though not impossible, that all the wealthy people ended up in one group and the not so wealthy in the other, or the vegans in one group and the omnivores in the other. Randomness is usually our best method for ensuring that our groups are similar before we give them any treatment. But the slight possibility that our groups might be really uneven is why it's important to replicate experiments. In some situations, researchers can also force the number of wealthy people or the number of vegans to be the same in each group. This is something called randomized block design. But randomness usually does a pretty good job. In our example, a treatment was either getting a cappuccino machine or not getting a cappuccino machine. In general, treatments are conditions that we want to test, like new medicines or educational interventions, like reading extra books to your kids. Treatments can also have levels. For example, when we look at whether exercise is related to weight loss, we might have three groups. One group does no exercise, one group does 5 hours of exercise a week, and the third group does 10 hours of exercise a week. These levels can help us see whether there's a linear relationship between our treatment and our outcome, or whether 5 hours of exercise is just as good as 10. One of the treatments in an experiment is usually nothing. These treatments are called controls, and they play a huge role in experiments. It's our way of pretending that we have a universe where there's no treatment. Let's say you got a little too eager to get your freshly baked chocolate chip cookies out of the oven, and you didn't put the mid on right, and you burned your finger. You put some Neosporin on it, and after a few days, your finger heals. You're so happy that you practically turn into Neosporin's next spokesperson. But it's possible that the burn would have healed just fine on its own. A control treatment, aka no treatment, would let us compare what happens between two similar burns, one treated with an antibiotic cream and one left to heal by itself. These types of control groups are great at helping us divide up the changes we observe into changes due to treatments and changes that are just due to time or circumstance. If your finger heals faster with ointment than without it, we can more confidently claim that there's a relationship between Neosporin use and burn healing than if we didn't have a control. Sometimes we want to control for more than just time and circumstance with our control treatments. With medical trials, you as the person taking the medicine would want new medicines to work better than nothing, but you also want to make sure that it's not just the act of doing something that's making you feel better. It's been shown that just the act of taking a fake medication or having a fake surgery, seriously, can make people feel better. These are called placebo effects. Placebos allow us to control these effects by pretending to treat everyone. Subjects in medical studies are often given sugar pills or saline drips to make it seem like like both groups are being treated. Non-medical studies also use placebos. Studies that claim first-person shooter video games like Call of Duty improve cognition should probably have a control group that plays a non-first-person shooter, like Mario Kart. Then the researchers can ensure that it's not just the act of participating in research or learning a new video game console that's causing the observed changes. Essentially, good placebos and controls should look and feel as close as possible to the actual treatment, so that the only difference is whatever we're actually interested in, like first-person shooter video games. Sometimes there are undetected factors causing changes in an experiment that we just don't know about. Well-chosen placebos and controls allow us to better account for them. Sometimes it's just not possible to shield subjects from knowing the difference between conditions. Take diets, for example. When people agree to be put into a clinical study which compares a group of subjects who do not change their diet to a group that goes low carb, it's hard to make both groups think they're doing the same treatment. People can see what they're eating. When subjects don't know which treatment they're receiving, usually because they're getting a good placebo, they're considered blind to the treatment. An experiment where subjects don't know what treatment they're getting, but the researchers do, is called a single-blind study, which leads to better experiments because all groups experience the act of being treated. But even in a single-blind study, it's possible that researchers might be biased when observing the subjects. The researchers still know which treatment the subject is getting. A researcher who spent years creating, funding, and planning a study probably thinks their treatment works. I mean, why would you dedicate your life to developing a drug to cure cancer if you don't think it works? The problem is that belief in the value of the treatment can cause researchers to subconsciously project those beliefs onto their subjects. In the 1990s, a group of researchers looked at almost 24 studies about whether sugar causes hyperactivity in children, and they concluded that, in general, it doesn't. Parents who thought their children were given sugar reported them as being hyperactive, but it turned out they were probably just being kids. When parents are blinded to whether their children receive sugar, both groups of parents reported roughly equal levels of hyperactivity. Even when we think our subconscious biases don't get in the way, they still sometimes do. We try to solve this problem by having double-blind studies in which both the subjects and the researchers have no idea which treatment the subject is getting. Just like with blinding patients, sometimes it's impossible for the researcher to not be able to tell the difference, but double-blind studies are the gold standard in many fields whenever they're physically and financially doable. And while we still can't bend space and time to make parallel universes, there are a few other ways to pretend we do have them. One is matched pairs experiments. Just like the name implies, these experiments use pairs of subjects that are very similar and give one of them treatment A and the other treatment B. Identical twins, for example, are about as close as we can get to a parallel universe. Since twins are genetically similar and often grow up in the same situation, we're able to get our treatment groups to be almost exactly the same, or at least way closer than random assignment alone. The more similar the groups are before treatment, the better researchers can spot treatment effects. We can also have a matched pairs experiment with non-twins. In this case, each pair is matched on one or more features that the researchers decide are important, like age, race, gender, or weight. Then these pairs are treated like twins. One is assigned treatment A, and the other treatment B. For simplicity here, we're assuming there are two groups. There could be more, but the best subject researchers can pair you with is yourself. Many experiments will give the same subject multiple treatments, one at a time, to see how they react to each. This ensures that each treatment group is the same, since it's all the same people. This type of matched pairs design is often called a repeated measures design. And while it comes with its own set of limitations, it can be better than regular random assignment. And sometimes the stars align and we get to see the results of the interesting experiments that we don't have the power to implement ourselves. Recently, the city of Philadelphia passed a sugar tax that would charge companies an extra 1.5 cents per ounce of sugary beverage sold. Researchers can't just assign cities to have extra taxes. When cities do vote these things into law, some very interesting things can happen. And they did in the Philadelphia International Airport. Because the airport straddles the city's border, some of those otherwise identical stores had to comply with the law, while others didn't. Through this data, researchers were able to find that, contrary to previous assurances, chain stores in tax terminals raised their prices about 0.83 cents per ounce more than their non-tax terminal counterparts, which means the tax did what it was supposed to do. increase the cost of sugary drinks, and encourage people to buy less. We all consume products that are the result of experimentation, from Amazon's web design to the prescription drugs we take, which is why it's useful to know why researchers feel like they can make the decisions and claims that they do. Knowing the theory behind experimentation also allows us to be more informed consumers. So the next time you find yourself staring down the homeopathic medicine section, wondering if that effervescent tab developed by an instructor of students will really stop your cold, ask how they tested it. Ask who tested it. DFTBAQ. You know, I'm not sure why this isn't taking off. I mean, where's my t-shirt? Anybody? Crash Course Statistics is filmed in the Chad and Stacy Imigholt studio in Indianapolis, Indiana.
Once again, as always, we get a good introduction, which kind of almost sums up everything I'm about to talk to. It gives you a good basis to maybe grow off of. So let's start in on the rest of the notes for the course. Now, we've talked about experiments before, and we've had the basic definition that it is under controlled conditions, manipulation of variables, so that we can collect data to analyze for cause and effect relationships. But part of this is that you have to design that experiment before you actually execute it to gather that data. You have to have an understanding of the steps and statistics. You have to have an understanding really of the background of the actual question you are looking at to be able to understand, well, what are things that are like other spurious relationships that could be part of your cause and effect that you want to remove to really isolate the one cause and effect that you are looking for. And this is why it becomes very important to take up your experimental design. Because an experiment is a process or study that results in the collection of data, and the results of experiments are not known in advance. We're not here to prove our hypothesis. We're not here to back up our hypothesis. We're here to test our hypothesis. And as such, this becomes a separate step where we try to remove our own bias and other external factors to show really what we're isolating and kind of condensing everything down to. And then based upon that data, coming to a conclusion to accept or reject the hypothesis after you've actually analyzed it. Now, usually statistical experiments are conducted in situations in which researchers can manipulate the condition of the experiment and can control the factors that are relevant to the research objectives. That if you're looking for the effectiveness of some kind of liquid when growing plants, well, then you don't want to have varying amount of lights and other temperature conditions that also affect plants that you would have learned from some of your background research into it. You need to be able to isolate those, turn those into controls so they don't become spurious reasons for the cause and effect that you're looking for in this specific experiment. So we need to worry about that controlled experiment. We need to make sure that we're setting that up and that we are properly dealing with finalizing that third step of establishing causality for non-spuriousness, that there's not other cases. And your controlled variables in a controlled experiment play a big role in this. So you want to, and becomes a big role of testing your hypothesis. And if you haven't set this up before, whatever conclusions you come to at the end can be attacked, and it breaks down the rest of your actual overall argument. And so a controlled experiment is a scientific test done under controlled conditions, meaning that just one or a few factors are changed at a time while all others are kept constant. Because again, if you're changing multiple things, how do you know which one was really having an overall effect in what you're working on? As long as we're dealing with just the normal sequential time of cause and effect view versus that cyclical that was mentioned earlier in the course. But we're keeping it a little bit simpler and going for the sequential view of time for now. Now, a controlled experiment is a scientific test that is directly manipulated by the scientist in order to test a single variable at a time. And the idea for this is, well, we're just manipulating that independent variable by changing its quantities. and then seeing what effect that has on the dependent variable by measuring what changes do we see. And we would have already set up a correlation before this, or at least established it, to say, okay, yeah, they were matched, and we know one comes before the other with a temporal factor. So now that we've got that in place, and if we properly control everything else and only manipulate one, and if there's a big enough change in the other, well, maybe we're still getting to a better argument that this is an actual cause and effect relationship that we're seeing, that we are actually establishing a causal relationship instead of just downgrading it to only a correlation between the two. That there's no really causation, they're correlated, but there's no real meaning beyond that. And really working towards that statistical significance that we want to show that it's not just by random chance that this happened, that there's a better probability that it was beyond that. And then we hope in the end that, okay, well, we've made our argument, we've answered it, and we've added to that pool of knowledge. And we hope that others that are looking at this same problem keep building up a bigger pool of knowledge related around it and strengthen that case for cause and effect. Because it's not just based upon one paper solely. It's based upon continual work over time and the body of knowledge that's developed from the entire group. So that's why we need to worry about the independent variable, the dependent variable, and the controlled variables and how we set them up. We know we need to have that in place. So we need to know what are our independent dependent variables. We have to know what are our control variables. We have to know what values we're going to set them at. And if we need to do multiple experiments, if we want to vary stuff and allow us to build up a basis of comparison to strengthen our argument or define specifically what direction it's going in. Now, beyond just the variables themselves, we can't just collect one set of data and then pull really any inferences from that. We can get a description of what's going on, but we really have to see what's happening in other cases and what's happening. So that now, with a controlled experiment, you need to expand upon what you're comparing the data against. As I was just saying, you don't just have the one set of data. You want to compare against, say, where you're not making any changes and collect that data. And then collect data for where you are making the changes. And then look to see, well, what's happening between the two of them? And so we need to expand upon our vocabulary then when we start talking about design for an actual experiment. So, in a controlled experiment, the study population is often divided into two groups. There can be more, what you're working with. One group is called the experimental group, or sometimes called the positive control, and it is the group where you actually receive the changes you're making. So if this was the experiment where we're doing the relation between size of a dog and how much they eat, well, in this case, your population is all the dogs that you're having to work, and you'd have one group that is dealing with, okay, if we're measuring how much they're actually eating versus different sizes and data that we actually have. Now, while the other group, if we're splitting this up, is referred to as the control group or negative control, and it receives the standard environment or conditions. So it's the same, you'd be applying the same control variables to it. You'd expect that you'd have the same independent variable, but you're not manipulating it. And you are measuring then the dependent variable of what happens when you're not making a change at all. Versus then the other case of the experimental group where you are measuring the dependent actual variable. So in a control experiment, the control group or negative control allows for comparison with other experimental groups or positive controls, so that you have a basis of where you're not making the change at all, and then measuring where you do actually make the change, and comparing what happens between the two of those cases. So many types of controls exist in various experiments which are designed to ensure that the experiment worked and to have a basis for comparison. So, in science, results are only accepted if it can be shown that they are statistically significant. And so, again, we've mentioned this before in the statistical reasoning notes, that for statistically significance, that it's not just by a random chance, that there's a high probability, very high, that when you're making this change, it's because of the change you made, and not some other random chance. That's that p-value and stuff that we showed from there. And to get these values, you have to compare it to other situations. You have to look at the overall data itself and see what's happening. And that's where we get to this point, like this chart on the side, which is a bigger thing, is that you start having two sets of data where you're doing all the measurements and you get two sets of statistics, your different means, medians, your ranges, your quartiles, all of that. And then you're comparing between the two of them to see, well, what has really changed? And is it big enough in the direction that we're looking for that we can finally draw that case of statistical significance, at least in the relation to this course, and see like, well, okay, I think this strengthens my argument based upon the actual data and analysis of what's going on. And so we need to make sure in our design that we take that into account in first, plan to have that, and then when we're executing it, go through making those groups, gathering the separate data, putting it all, and getting ready for the analysis phase. So again, statisticians can use the difference between the control group and the experiment group and the expected differences to determine if the experiment supports the hypothesis or not, and if it's just by random chance. So we've expanded. We can't just have just or independent dependent variables and defining our control variables and what they're set to. We now have to think, okay, well, what is the population we're really looking at to? How are we going to be sampling from there? And if that's needed, and even from that sample, that entire population, how do we then decide upon how to divide those into the control group and the experimental group, or multiple groups if needed? And then how are we going to properly gather that data itself? And so this is where we need to expand upon our experimental design and decide what to do. Because sometimes it's easy to break it up into groups. Sometimes it's not so easy to separate from the groups because of other factors that we're not expecting that could come into play. So that's why I have these next few slides, is just bringing up an example of some other designs where maybe we can't separate the groups, but where we can then instead think about in time that we work with the same group, but we take multiple different measurements over time, changing things, the before and after kind of case once they've gone through the experience, and using those as our two groups of comparison. In this case, and again, this is not all designs, this is one thing you could do, and like sometimes works good with people, and there's other cases, and there's other types of designs you can go through. But in this case, this is referred to as repeated measures design. So a repeated measures design is a research design that involves multiple measures of the same variable taken on the same matched subjects, either under different conditions or over two or more time periods. For instance, repeated measures are collected in a longitudinal study in which change over time is assessed, maybe say from young age to adulthood, and the overall effect that that actually has. So it really depends upon design of your experiment. And sometimes you're going to have to dig deeper into this to realize, well, do I have to do a repeated measures design, or are there other experimental designs that I should take into account? So fun. So other examples of this, you can see here. What if it's something to deal with blood pressure and maybe an exercise and the effect that that could actually have? And you could do things of taking the measurements, the blood pressure before an event A, then applying it in time point 2, and then taking another measurement in time point 3 and see what's happening. And then these measurements that you're taking at that time from the overall group become, okay, I have the first group, so maybe the control being the very first one where nothing's happened, they haven't done any work. And then having the middle group where they're being stressed, and you can gather the data, and that becomes your group 2. And then you finally have afterwards your group 3, and you can compare all of them to see what's going on. Another good example, tasting food. Having the same people and not separating it into group 1 to only feed them chocolate cake, or group 2 only feed them carrot cake, or group 3 only feed them lemon cake, or so forth. And having those all separate groups and determining who type of people and what cake they like for some reason. Well, maybe instead of better design repeated measures is just kind of like, well, use the same group of people, but have them do like, hey, step 1, evaluate chocolate cake, take those data measurements. Step 2, next cake. Step 3, next cake after that. And the idea is that each one of these steps becomes a point where, okay, you kept everything else the same, kind of keeping it controlled, but then you varied the type of cake, which maybe could be your independent variable. And in each time you've taken measurements before going on to your dependent variable, and you can compare all of these to themselves overall. And depends upon the experiment you're working on, but this is just an example of a different type of design you could do if you can't easily just split the groups in the beginning and you're stuck with one group, but you would still like to have a control set of data and then your experimental groups of other data from there. Now, mentioned just a short little time ago is that, well, the basis you want to have, at least bare minimum for an experiment, is a 2 kind of group design of a control group and an experimental group. And you can expand upon this depending on what you do of having multiple actual other groups, and really where you'll generally still just have one control group that you're working on, and then you'll have multiple experimental groups, which are variations of the actual independent variable. So a 2-group design in experiment involves only making one change to your dependent variable and having 2 groups, so controlled and experimental. The experimental group and the control group, sometimes positive control and the negative control. 2 names for them. In a multi-group design, experiment involves making multiple changes to your independent variable where each change becomes its own experimental group. So this is the case, not that repeated measures where we only have one group and we're getting separate sets of data. This is where hopefully we could actually split them all up as the overall data, and then they become their independent separate groups. And this is in relation to your population, which remember here doesn't mean just people. This is whatever is under study when it comes into relation for statistics. But you will still always have that control group. So a 2-group and multi-group design are both valuable, but they answer different questions. So bare minimum, a 2-group design tells you whether your independent variable has an effect at all, while a multiple group design tells you how much of an effect each level has. So, in a 2-group design, you have your control group, where you're not making any changes, and you actually have your experimental group, where everything else, between all of them, the environment, everything's been kept the same between the two, but you've only, in the 2nd group, made change to the independent variable, and then you can measure both sets of data, comparing them using your powers of statistical reasoning to test for statistical significance, and see, okay, well, how big of a change went on here? Whereas adding in multiple other experimental groups can see, well, what level effect does this have overall? And then seeing, okay, well, that could strengthen maybe other possible spurious cases you were thinking of and give you more direction of how to actually work. So this all depends upon the context and background you're doing, the area you are in science. So the more you delve into this and the more you research of how to do proper experiments, this becomes more refined depending on the area you're in, but we generally start having that 2 kind of group basis to start everything. So a quick example before we go on, and this is more of a historical one, that shows earlier days of scientific method. We're not getting to the exact levels where we are today, but seeing, well, okay, well, how was this kind of scientific reasoning used and logical reasoning used to break down and actually solve a problem based upon what you're seeing? So, tall ship here. Now, in the early 1700s, the world was a rapidly expanding place, especially due to, ocean travel. Ships were being built and sent over the world, carrying thousands and thousands of sailors. These sailors are mostly fed the cheapest diets possible. How lovely. And not only because it decreased the cost of goods, but it also because fresh food was very hard to keep at sea. Probably many other factors. And you can see where this is leading, that not the best of food and other conditions. What does this do for health? Today we understand that the lack of essential vitamins and nutrients can lead to severe deficiencies such that manifest as a disease. And one of these big diseases from that time was scurvy. Now, Now, and it's a big, I know I'm making a joke there, but scurvy is a friggin' horrible thing. So scurvy is caused by simple vitamin C deficiency. But we can use those terms nowadays because we're used to the terms vitamin C. This came out of other research in other areas, deficiency, and like what that importance of it, and something that we're used to getting all the time. But you think back then, if you didn't know, and the cheapest food in storing this and what you could get, again, can be low on something and start causing problems. The effects overall of this, like lack of vitamin C, scurvy, is brutal. Although early symptoms just included general feelings of weakness, the continued lack of vitamin C will lead to breakdown of blood cells and vessels that carry the blood, which, is just slightly, and I'm saying this very sarcastically, just slightly important when it comes to our systems as a human at all. The results in blood leaking from the vessels. Eventually, people bled to death internally and died on the sea. How lovely, and that's just from not having vitamin C. But this time, they didn't know. Like, there's so many ailments, and there isn't the medical knowledge that we have today, and they're still trying to figure this out in this earlier times that became the basis of a lot of what we know now. They didn't know, and how are they going to fix this? And this is important if you have a lot of sailors dying, and this is a strong factor of change within your society and importance of it, like say with England or Spain, Portugal, all that fun, then like, how do you deal with that? We need to deal with it. So before controlled experiments were commonplace, a simple physician decided to tackle the problem of scurvy, and basically was doing somewhat of a controlled experiment, using that logical kind of reasoning, breaking down, having these separate groups, and isolating to see what was actually having an overall impact. So James Lind of the Royal Navy came up with a simple controlled experiment to find the best cure for scurvy. He separated sailors that with scurvy into various groups. So you can see in that beginning, scurvy, what's actually causing it, what could be a cure, so gathering people who had those symptoms. Again, you always know there's ethical stuff we could think behind this, but if it helped, you'd hope this is good. But we've talked about that before with the science journalism and Henrietta Lacks and ski experiments and all that fun. So, okay, back to this story. He subjected them to the same controlled conditions and gave them the same diet except one item. So right there, gave them the same diet. He's talking about control variables. That right now, knowing between cures, and if it's something that you could consume for nutrients within your body and adding to it, that keeping them on the same meals and all of them will hopefully deal with the spurious case that it was some different food that was having an overall effect. If all of them were eating the same thing, to begin with, that's the control part. And then just varying one thing from this. So each group was subjected to a different treatment or remedy taken with their food. So what you start having there then is there's not really this control group to compare against. It's just a whole bunch of experimental groups where your independent variable you're manipulating is the different item of food that could be a possible cure for scurvy as they test this. Because everything else they're eating between all of the groups is the same. And group A, say of 5 sailors, was getting limes or oranges or whatever. And group B was getting something else, barley, water, cider, like whatever else from there. Then you have all these separate groups and seeing, well, which one started showing better cases for them actually curing, and which levels, and that kind of combination and narrowing that down and find that group. Well, if this worked best for this group and there's enough sailors within it, proper sample sizes and all that, you'd hope, well, then maybe we can extract this and start including this overall. So this created the first clinical trial or test for the effectiveness of a certain treatment in a controlled experiment. There probably could be others, but this is just a good example of earlier days, before this was a commonplace thing to do. So Lind found that the oranges and lemons helped the sailors recover fast, and within a few years the Royal Navy had developed protocols for growing small leafy greens that contained high amounts of vitamin C to feed their sailors. Now, okay, so clinical study, and it's also an example why something that seems so small for citrus and stuff like this become such a huge thing beyond just ships for a Navy to actually deal with. So, but you get the example of those different experimental groups keeping things the same, only varying one, and seeing what was the overall end result. So here, stats weren't really being collected other than who was getting better overall and what was discovered from there. So fun. So, experimental design. So stepping into that a little bit more beyond just this controlled experiments, we know we need to have those controlled variables. We know we need to set up a control group with at least an experimental group, and then decide upon, do we have multiple other experiment groups? And then deciding, okay, well, can I actually have all these different groups, or do I need to do a repeated measures kind of design? And does that fit properly with my project? So part of your background research may either be to delve deeper into this or talk to someone with more experience with this overall design. So experimental design is the process of planning a study to meet specific objectives. Planning an experiment properly is very important in order to ensure that the right type of data and sufficient sample size and power are available to answer the research question of interest as clearly, as effectively as possible. And really that non-spuriousness, that if you have a proper background with stats and proper research into knowing different forms of experimental design and controlled experiments, and if you set this up properly, then the data you will gather will be backed up stronger, and the analysis that you do from there will also be backed up. But if you don't do a lot of these things properly, you can still pull the stats and do the comparison, but then your overall argument is just weakened. You didn't gather the right data, so those final numbers that you're drawing aren't right. And if someone else is validating this, you could be challenged on it, which would be good, having to see what the overall community is vetting from this and how this changes over time. And we hope for the actual overall best, backed up by the strong logical argument reasoning that we have put together by following the scientific method. So experiments. So for example, say a rental car company compares tread wear of 4 brands of tires while also controlling for the type of car, speed, road surface, weather, and the type of driver. And so you can see, well, they're varying the type of actual tires. That's your independent kind of variable in the manipulation. You'd have separate groups for those. Between all those groups, you keep consistent the vehicle, speed, and like all these things that would also have an effect on that. And so it's very important for the design that you define that beforehand to strengthen your argument. Now, there's many ways to go about designing an actual experiment, and some of you probably have more background with this, but for this course, I want to set a basis of what are some basic steps you can go through to actually get ready for designing your experiment before you would go to actually executing this. So I'm presenting these kind of basic, high-level 4 steps that you could follow, that by the time you're done doing this, and if you set it properly, then after this, you just execute following what you've made, gather the actual data, and then once you're done that, go into the analysis phase. And so step 1, you would have done this a lot before. And so we'll talk about that more in the next slide, and I'll go through each one of these in more detail. But really it follows from there, knowing the question, knowing really what is the population that's in relation to that question properly. We saw that previously with the statistical reasoning notes, that you're defining the proper population. From there, knowing, well, do I need to sample or not? Am I able to look at the entire population, or is that infeasible? And then do I need to take some kind of sample, and how do I do that properly? And then breaking down the experimental design of what groups you have, what are the actual variables, what are you setting them to, and the specific procedure you're going to go through to actually collect that data itself. So let's go to step 1 in a little bit more detail. Now, step 1, I've got a lot of stuff here, but this is a lot of what you've done before from the beginning, that you'd have asked a question, done that background research, and gotten to your actual hypothesis and predictions before you're getting into this experiment. So this would kind of overlap. Like when we're doing those first steps, we'd also want to be thinking about, well, how are we going to do our experiment? And while we're doing our background research, we can dig deeper into that and understand the problem and understand the context better to know what are better things that we should be putting under control and limiting, and maybe how we should be refining our question or hypothesis before we go on, and key parts of things we need to know from an actual experiment. So collecting that data, like we need to identify the sources, variability, what are other conditions we need to put into place. We need to understand that. And we saw that a little bit before in that kind of student experiment design when they were looking deeper and then realized, oh, well, certain other things when we look into color will affect stuff, and having to set up proper lab procedures and experiments. And was that feasible within that situation? Using that to kind of draw some conclusion from there. And so all of this stuff involved a lot of that background research and would play a key role before we would go on. That we've got to understand that problem properly. We've got to understand stats properly to know that we're asking the right questions and looking for the right data. And that's what comes to like this next step too, of define the population. Is part of that background research, you want to be looking into what is the population that you really care about. And remember here, population is a collective, not just of like people, unless people are your subjects, then yeah, but it could be animals, plants, items, stones, like whatever is the key thing you're actually looking at, and realizing, well, what is the key population? So based on the question, what are the key aspects that bring all these elements together and refine it specifically as the population you're looking at? Like, is this the population of the world, of Canada, of Calgary, of just Mount Royal? If we're looking with people and narrowing that down and the right population that fits and making sure not to over-bias what you're looking at and encompasses the larger group. And so you need to understand this, defining what you're working with, what are the members. And you should be documenting this in some way and making that clear in your actual communication phase at the end. Unless it's something that's presumed that you already know that's within the actual community of researchers or who you're working with. So, like the entire population then becomes what you're trying to draw conclusions from and focusing your experiment on and going deeper into those phases. From there, determine the need for sampling. If you know the population is something that's a little bit finite within a specific number of steps, and that you know that, okay, this is not overly exhaustive to go through every single element of that population that you've set up, then, well, okay, you don't need to do sampling. So, example where you do the entire population, maybe it's with plants, and you decide upon, okay, I'm going to get 100 of the same plant. And then, well, okay, that's the population. Like, I'm not looking at the entire population of the entire world, but at least if I get large enough size of that sub kind of plants that I'm working with, and not consider that exact realm. So, basic example, probably not the best. But, you have to determine, look, okay, well, is this feasible? Is it economically feasible? Can we do it within time? Is it possible to look through every single one? And if it comes up in any case where it isn't, well, then you've got to deal with, I need to do some kind of sampling. You need to worry that you're focusing it on the right sample, that you're drawing the right conclusions, inferences, and you're not taking it too large or small. Which brings us to stuff that we talked about in statistical reasoning, is things like the sampling method of how you're going about collecting that sample so that you're not introducing bias. So remember, that was that probability kind of sampling or non-probability sampling kind of family of methods, and there's specific ones that are then drawn down from there, once again showing logical tools that you may not know how to do, but you can look that up and look up sampling methods, look up the right one maybe under probability sampling methods, and learn more about how to do that. And then also determining the proper sample size. If you know how to calculate it properly, getting a rough estimate or using a built-in calculator and hopefully getting close. If you don't have a lot of experience, just plug in and play around, dig into the numbers a little bit more if you feel like it, or just use it in its basic settings as a starting point that you at least be closer. And this is for beginning entry-level versus where you get more experience and you would know how to do this as someone who's more ingrained from the culture and learning from others. And so you must determine those things. But before going on, I want to go through another video that kind of blends together the sampling kind of methods and experimental controls and how you could start splitting stuff up and hopefully give you an idea of how to do this yourself.
In this video, we will be looking at experimental designs. The types of experimental designs include the completely randomized design, the randomized block design, and the matched pairs design. In a completely randomized design, each experimental unit is randomly assigned to a random group to receive a different treatment. Each unit in the same group will receive the same treatment. and at the end of the experiment, you will compare the results from each treatment. Show how a completely randomized design would be used in the following example. A researcher wants to conduct an experiment to determine which environment is best suited for studying: a library, in one's own room, or outside. A total of 30 university students volunteer to participate in the experiment. So we have 3 treatments: the library, in one's own room, and outside. Since we have 3 treatments, we will have 3 groups receiving the treatments. Since there are 30 university students, these 30 subjects will be randomly assigned into 3 groups to receive the treatments. Since there are 30 people, each group will have 10 people, and at the end of the experiment, we would compare the results from each treatment. Let's say that the researcher believes that gender has an effect on the results. In a case like this, we would use a randomized block design. A randomized block design doesn't immediately randomly assign experimental units to receive treatments. We first assign people into a block based on a characteristic that is expected to influence the response to the treatments. In this example, gender would be the blocking variable. So first, we separate our experimental units based on gender. One block will be for females and one block will be for males. There are 18 females and 12 males. Then, the experimental units in each block will be randomly assigned to 3 different groups to receive a treatment. So let's make a diagram out of this. We are looking at a randomized block design, and gender was the blocking variable. We started off with 30 university students, and we separated these students into 2 blocks. One was for males and one was for females. We determined that there were 18 females and 12 males. We will have the females be randomly assigned to 3 different groups, and each group will have 6 females, and each group will receive different treatments. For the males, we are doing the same thing, except we have 12 males, so we will randomly assign 4 males into each group. And at the end of the experiment, we will compare the results within each block. The last type of experiment we'll talk about is the matched pairs design. In a matched pairs design, we are only comparing 2 treatments by using the same or similar experimental units. If we are using the same experimental units, we could have an example like this. What type of gasoline is more efficient? Type A gasoline or Type B gasoline? 3 cars will be used in this experiment. Describe how a matched pairs design would be used. If we are using the same experimental units, then each experimental unit will receive both treatments. So we have 3 cars, and each car will receive the 2 treatments, one with Type A gasoline and one with Type B gasoline. We would use the same car for each treatment, and which treatment goes first will be random. So for example, we could drive with Type B gasoline first, then once all the gasoline is finished, we would fill up the car with Type A gasoline using the same quantity, and at the end of the experiment, we would compare the efficiency of the gasoline. There are cases when we can't use the same experimental units for a matched pairs design, and we would have to use similar experimental units. For example, a researcher is trying to determine whether or not sleep deprivation has an effect on test scores. Describe how a matched pairs design would be used. Well, we could try giving both treatments to the same experimental units like we did in the other example. In other words, we could have the same person write the test on 2 different days, one being sleep deprived and the other with sufficient sleep. The problem with this is that we can't have the same subject write the same test because they would know what's on the exam when they write it the second time, so that would be kind of unfair. Instead, we could start off by pairing up students with similar GPAs. So for example, the 2 students with the highest GPAs would be matched up together, and the 2 students with the lowest GPAs would be matched up together. Then, each pair will be split up and randomly assigned to one of the 2 treatments. So for a pair, one person will get the sleep-deprived treatment, and the other person will get a normal amount of sleep. Then, we would compare the results for each pair, and we will also compare all of the results. So for example, if we saw that the sleep-deprived people were consistently getting lower test scores than the people who got a regular amount of sleep, then we can say that sleep deprivation was actually the cause for a bad test score. So let's quickly recap. These are the experimental designs we talked about. In a completely randomized design, each experimental unit is randomly assigned to a random group to receive a different treatment. This is what the diagram would look like. Group N or treatment N means you can have any number of groups or treatments. A randomized block design first assigns people into a block based on a characteristic that is expected to influence the response of the experimental units to the treatments. Then, a completely randomized design is performed within each block. This is what the diagram would look like. Block N means that you can have any number of blocks that you want. For a matched pairs design, we saw two scenarios, one that uses the same experimental units and one that uses similar experimental units. Both of these involve the comparison of only two treatments. If you are using the same experimental units, each experimental unit gets both treatments. This is what the simplified diagram would look like. If you are using similar experimental units, we first pair up similar experimental units, then each pair is split up and randomly assigned to one of two treatments. This is what the simplified diagram would look like.
Okay, so I hope that helped give you more of an idea of, again, these different cases of design that could come into play. Now, as someone who, if you're junior to doing this, and you're not sure exactly what direction to go into, then that's where you would want to talk to someone who's related to the experience, the context, and has more experience doing that. And if nothing else, at least if you know that these exist, you can research them more, pick one that you at least feel now would work, and then just keep stepping forwards from there, because you're going to learn by whatever you do with that process. So, after this, we said is now combined with that experimental design, we're stepping into defining the groups, getting more into those control variables, and then setting up your actual procedure. So, when defining your groups, you must at least have a two-group design bare minimum. You know you're going to have that no matter what. So one being your control group, where everything is the same, and then not everything the same, is just that one control group, and you have experimental group, and you're keeping the conditions the same, but in the experimental group, you're manipulating the independent variable. And then maybe you want to decide that you need to have a multi-group design and narrowing that down, and then you'll add extra experimental groups. You combine that with the experimental design, your sampling method of how you distribute those and how you're going to go about collecting that actual data. Because whatever experiment procedure you follow, you're going to be going through that with each group. And then you want to make sure that at least when you're doing sampling, when it comes to a lot more science, is try to stick to probability sampling to form your groups. And that's in a science context. In a social science and qualitative design, well, that's maybe where you could still apply probability sampling, but maybe where non-probability sampling can play a better role. So right now, stick to probability sampling and dig into one of those methods to go deeper. Now, you also want to determine all your control variables at this time. So you would have been doing a lot of this before during your background research and other things that could be other factors that come into play, and defining all those. And then here you want to really define them, and you want to say what you're setting them to, and you want to have that communicated. You can't just keep that hidden to yourself. You've got to communicate that at the end. So if someone else is going to repeat this, then how are they going to go about doing it? You want to determine the actual values you're going to assign those to. So based on the background research, you may have a better feel, you may have an understanding from there, and if nothing else, well, just pick at least a reasonable value that you learned from your background and say, well, you can state that as an assumption, especially if you're a junior person doing this, that, well, this is based upon the research I have, this is the best feel for it, and then just state what it is and go forwards from it. And this action increases the validity of the results by reducing extraneous sources or variations from external data. So you have your other confounding variables, your spurious cases, things you don't want. And you're trying to do this to the best that you can now, and hopefully refine it more in the future if this doesn't work out. Now, other things that you could bring into play that we've seen in the previous videos to remove some of these cases, depending on what you're working on, is to bring in blind experiments or double-blind experiments. And so remember that blind experiments is where some of the information is withheld from the actual population. So this is going to be more with people that are actively, consciously knowing and then could react knowing more information from it. And if both groups don't realize if they're the experimental, positive or negative, then you get a better inferences from there, as long as this is all ethically and properly done, and not like some of the earlier Milgram experiments from psychology, if you look into them. And like the case for double blind is then, well, maybe there's a bias or something that the researcher themselves can have with it, and so to distance them from the actual, distance themselves from the actual scenario, that some the participants in the population do not know some of the information, and then the actual researchers themselves maybe are not connected to the actual people. An example would be if I was doing research on effective education practices, say with my own class, and I've got to remove myself from part of this is because, well, I am in a position of authority or power in deciding grades over the students, and if they're the subject or population that things are being looked at, that's going to affect how the students may react. Maybe they really hate me, maybe they really like me, or maybe they're concerned if they don't react positively that this could affect the actual outcome. And so you'd want to get a third-party person that's collecting the data, anonymizing things so that even when it comes back to me, I have no connection to knowing who and specifically this was coming from, and we know that we've removed any power dynamics that come into play, and hopefully be able to properly isolate the factors of, well, of these new conditions of how stuff is being presented or done in classes. Is it being more effective to how people are actually learning? So this depends. So when it comes to blind experiments, double blind, if you're working with people, it may be a good condition that maybe something from the blind or double blind may come into place. Depends on the actual context. We'll see in the future when we step into the specific case for this course. Now, finally, after all of that, if you've got this in place, your design, you know what you want to do, then you want to go through doing, well, what is your experiment procedure going to be? Like, what are all the steps that are going to be followed to actually collect that actual data? Now, some of these are community data. Other people maybe keep this internal. If this is a junior person, like we're assuming from, say, course like this, GNED 1103, then, well, you should be detailing what are the steps you're going to go through and being very clear about that, of how you're going to measure that, so someone else would be able to repeat this. And so it's something that you're going to have to do with the course overall. So way back when, in Scientific Method Part 1, we saw this quick example when they were testing different brands of batteries for their quality. So they're keeping all the conditions under the test the same of the same devices and trying on different devices and some of these steps, but they're just varying the independent variable being, okay, well, the types of actual battery. So in this case, they're not really having a control group to compare against. They're just going, what's the type of battery is best. Each experiment group then becomes a different battery that's being tested. And in each one of them, they're going through these exact same steps that you see here to actually test it. And from here, gathering all the data, keeping all these points, and these become your individual data points that you then calculate the statistics off of, and then start drawing your conclusions to accept or reject your actual overall hypothesis. And boom, we're back to this. We're back to the chart that we've seen overall of like asking the questions, and we've been focusing more down here of this procedure and troubleshooting, and hopefully that we're getting this right for our actual collection of this overall data. And once we leave this process, and we've done everything for design and experiment to the best of our knowledge we have now, and we actually go through executing, and we have all this data, and we've calculated the general statistics that we need, then we'll go into the analysis phase of looking at those actual statistics, maybe drawing more inferences from it, or adding more to them, or different types of charts, and coming to some overall conclusion, as long as we've set everything else up properly before. And so that's what we've seen here, is that if we have these two groups, if nothing else, at least seeing the condition where, boom, nothing's being changed, versus the actual case for experimental group, and comparing between these two data sets and drawing what is the difference between them. And so that's what's going to be important, is we need those overall differences and being able to compare them. Now, will we be perfect within this course? Well, no. Like, this has been a 6-week course, whatever, equivalent to like 1 semester, and to be a course and giving you a feel of getting into being part of that culture and knowing what you do. And if you were to do this more and more in the future, and if you're going deeper into a science degree, well, then you're going to experience more from this. If you're going to other degrees, we'll be aware of how could I adapt this process, or how could I challenge this process, or how I could see that it's affecting me, and knowing these two different groups. But for us in this specific GNED 1103 course, I just want you to kind of dabble in it and not feel so fearful of trying to do quantitative reasoning, and have some basic steps, which I'm going to apply here. It's not going to always be perfect, but I want people to really show me that you were trying to attempt to do this and build up and backing it up with numbers and data. And you don't need to be perfect at it. You just need to try making an argument based upon what you see and the proper definitions from there, and keep doing this and practicing and getting that feedback. And so, like we see here, like this box and whisker diagram, which is helping us one way to visually descriptive statistics sum up what's going on. And so, like, you're drawing conclusions, and so you're building up your argument of what you're going for, checking for your statistical reasoning, accepting or rejecting the hypothesis. And so for us here, really what I'm going to suggest is a rough way to go. You can go whatever you want. If you have more background in stats and you've taken that before, go ahead. Go ahead and make those arguments and go with the practice. If you don't have as much of that background and you want something to roughly follow and like build upon, then we'll try to follow what I have here. Some basic steps of 1. What's the number line? Like based upon the data, what is the starting and ending points that I should see for my number line in comparison? And if you're given things like the min and max, there you go. Well, pick some values smaller than the min, pick some values larger than the max, and you have your starting and end point for the line, and then equally distribute up your measurements from there. And make sure you have your box diagram ready to go. Next is to look at the context and think, okay, well, if we have the number line of going smaller numbers here to larger numbers, so smaller to the left, larger numbers to the right, well, then when we're in the range of left, like where is it good? That smiley face kind of diagrams I've had before. Where is good? Is it like lower numbers are indication of something good, or larger numbers are indication of something good? And you need to know this later on. If you're looking at the skew, where the numbers are, where do they lie, what tells you what is that good nature? So you want to define that based upon the actual context you're looking at. After that, draw some charts. Get your stats going. Draw the box and whisker diagrams that we've had for this diagrams. Like, I'll always give you the standard deviation, all the rest of these kind of data, and then, well, you should be trying to draw that into a chart to visually see what's going on. And maybe taking all your different groups of your control group and your experimental groups and putting them all into one chart and having some kind of easy way then to visually compare them. Because at least then you can start seeing, well, if they're all along the same spectrum, they're all been measured, we're off the same control kind of conditions, and you're just varying one thing, then how did some data shift to one different side and by how much? You can visually start getting a feel for where stuff is going. You then should go through each one of those actual charts and look at the distribution of each data set. Is it a normal distribution, or is it skewed enough in one way, to the positively and negatively skewed? And that tells you, well, where is the data lying and where is it clumping around for that rough general large peak, and also gives you some idea of, well, what's the next measures of centrality should I use? Should it be the median or should it be the mean? How should I combine this together? How does the mode come into play? Should I be sticking then of using like the range and then maybe the standard deviation, or combined with the mean, or do I go with the range and the interquartile range and go with the median as the main kind of thing to back up my argument, with the rest of it being like secondary of like, well, okay, if I'm using the median and the interquartile range and all the other values in that, well, then maybe I can compare it against the mean, like the mean and mode, and not worry about the standard deviation because we don't have a nice normal distributed curve. So you need to decide which then becomes your main like statistics you're going to look at to compare. And then you can compare each one and see, well, what's the difference? We're looking for that statistical significance. And normally this would be like t-test or p-test or chi-test, like other tests that would calculate it based upon the actual data. But for this course, we're not going that deep. I just want you to play with it a little bit and look more, well, is it a big enough difference? So based upon the context, what's going on? As you're comparing all the data, what's the difference? So maybe you can even just start subtracting and getting the actual difference between the medians of each, or the means of each, and the interquartile ranges, and what is that difference, and maybe document those down themselves so you can use those exact numbers in your argument and be more quantitative in your actual argument. Instead of being vague like larger, you're saying larger by how much, or smaller by how much. And for all of that, checking for that statistical significance idea. That again would normally be calculate your p-value and have an exact thing. You'd be stating this beforehand, but for this course, since we're not going as deep into calculating those and working with them yet, we're going to mimic it and simulate. And the idea of just worry about how big of a difference is it big enough to draw any conclusions? If it's too close, we're still only in that correlation realm. Maybe we haven't fully established causality, but we've still learned something, and we can then go innovate and create new ideas off of it. So you want to compare your specific data and see, well, based upon the context, what is the largest difference? And, every context is going to be different, but I want you guys to then say, well, if you're going to say if it's different enough and conclude that it is big enough that you consider to be statistically significant, logically, you have to explain that. Like, you need to explain why you think that difference is big enough and looking at the context. So, say if this is a course and we're talking about percents and there's a 10 to 20% difference, maybe argue, well, a 10% is a big enough chunk. And you can just state that for this course. They believe a 10% is a big enough chunk to show that this is a big enough change, and looking at all the variables and seeing that consistently, is this, even if they overlap, is it really showing a big enough change what's happening? And then what you have done before this, so by having the charts, by going through the difference, and by describing each one, you're backing up your argument and using the words of like why you think it's large enough that there isn't actually been a change between your actual groups. And that becomes another bigger premise for your final step of getting to accepting or rejecting your hypothesis of like, well, what's going on? So it's a fun part. So we'll have another case study, an example of this. We don't have too many more slides here. And as we're like nearing the end of the course for the main stuff for science, before we get into our other main topics, thinking how we can innovate off of new ideas of asking a question and then validating, going through this, the scientific method. Now, we've seen this before. I'm not going to go into this context here. We've seen it in statistical reasoning, part 1. We've seen it in the examples from right here. And this is just one to dig into that, of like looking into that context, getting the actual number line that you see here and knowing, well, okay, what's good or bad for this specific context, and then going through and drawing the overall charts, and then, well, okay, based upon this, start looking for the max and min. Well, we can subtract the maxes, we can subtract the mins, we can subtract the medians and these interquartile ranges and see, well, what is the difference? And is this big enough from right here, from one group versus the other, like the control group away from the highway versus like next to the actual highway? And what does that say for this overall context? And back that up and get all the numbers together and see if it's big enough, and then come to our final conclusion, which brings us back to almost one of the last times you'll probably see this, but this chart of like where we started in the beginning of the course of asking questions, which anyone can do, and coming up with that and innovating off of it and looking back to previous research and like, okay, doing background research, and then from that refining your ideas, maybe going back and reinventing what you learned from that for the question you're looking for, and then stepping forward through this process, and each step kind of changes and digs down deeper, makes you ask more questions, makes you build upon this actual data and back up your actual argument till we've gone through the analysis and coming down and communicating these so that we can document it. And through this whole process, we would have been documenting, keeping this, and the fact that when we write it up, it's going to end up being in the same way, leading someone else through our argument of the first question down to the actual communication of the actual results of how did we get to this point ourselves? What is our logical reasoning that we came to this through inductive, abductive, and deductive reasoning, and like building up all of our premises to build up our overall larger deductive argument for the end that may be valid as far as we've gone through our steps, and we just need other people to reproduce this to say that it wasn't just us, that other people are seeing this and building upon this knowledge and hopefully opening up something. And if nothing else, for the person doing it, innovating and growing off these ideas, because I know anytime I've gone through a project like this, that by the end, I have new ideas that I didn't think about before that I can then grow from, that's backed upon other experiences that can keep growing and digging deeper as I keep going through this process myself and modifying it as we go. So after this, it's just going through some more case studies to give more examples of this, and then digging into our main topic for the course and how could we innovate from that, and any of us in this course, and then taking the scientific method and digging down a little bit deeper. Okay, from there, as always, like to end, I think as I've done the most videos for this course, is make sure to take care of yourself and the others around you. Small acts can make a big difference. Like, You never, you never realize what even the smallest thing you could do could make a difference. And one, making sure that you're not drained, you've taken care of yourself, you are in a good place, and then stepping up where you can for other people's in your community, and stepping up for the ones who maybe don't have a voice to speak for themselves. And I know I'm going off topic with these notes, but it's poignant at any point in time that you're watching this, to take care of other people around you, take care of those that are in need. Take care of yourself that's in need, and communicate with everyone else. And then hopefully we can make this world better for somebody, as I hope to do for people in this course. Other than that, I hope you are all doing good and that you've learned something new today, hopefully.